Good morning. If you guys want to drop your name and organization in the chat to introduce yourself, you're welcome to. Um, we are going to give it just another minute for people to hop on. We've got a steady stream coming in. Might start in a minute. All right. It gets slowed down. I'm going to share my screen.
Yeah, then I can ask you to change it. Yeah. So
Okay. Yeah, so I'm going to start with this. And I should still be able to. Is There it goes. My computer's just being slow. All right, can you guys see my screen now? All good? Yep, okay, great. Thank you. All right, so thank you all for joining us. It's great to see um, a lot of people coming in, a lot of new names. I am Trish Porter. I am the Director of Programs and Communications at Resilient Virginia. And if I stop talking for a brief second, it's because I'm letting somebody else in. So bear with me here. But we thank you for joining us. This one. Um, I didn't put an agenda slide because it's really, we're going to introduce ourselves. Dr. Younos will give his presentation and we'll have Q&A. So I just wanted to start with all these new people, um, letting you know who we are real quick. So we're a statewide nonprofit, and we catalyze collective action to enhance the systems level resilience across Virginia. We connect people, resources, and ideas to create more resilient communities. Um, Again, sorry, let me let somebody in. Here we go. And we do this through different platforms. We have a resilience learning and leadership lab. This is part of that, the Spotlight on series. We have a resilience academy. And in 2026, we're launching a Resilience Foundation certificate. We've got a biennial conference. We have an RVCA, the collaborative, and Be Resilient Virginia is launching in 2026 as well as an interactive way, a website for connecting and finding information about resilience. So our vision is to empower that empowered communities exceed resilience benchmarks and embody whole community resilience. Um, we have four pillars that we work on: ecosystem services, environmental, sorry, uh, ecosystem services, economic activities, buildings, like the built environment, and then community action. You can learn more about us on our website. I kind of flew through this because I really wanted to get to the bulk of the call. The reason for this webinar was Dr. Younos's presentation. He's the founder and president of Green Water Infrastructure Academy. And do you want to try one more time, Dr. Younos, to share your screen, or do you want me to just keep going?
okay, why don't let's keep going. So yeah, I can ask
Okay,
you to yeah. So
I
yeah,
can do that. Yeah.
yeah. Okay. Good morning, everybody, and thank you for being here this morning. And I'm with Green Water Infrastructure Academy. Please change the slides. Next slide, please. Yeah. So the mission is enhance human health and quality of life in global urban environments by promoting green water infrastructure research, education, and outreach programs. And so there are goals, and one of the goals is to offer seminars and workshops and host symposia. So today is kind of the goal is to do this webinar this morning. Yeah. Yeah, go ahead, please. Okay, the webinar content. Climate change science, I'm sure most of you are familiar, but I just gave a brief overview of climate change science. And then we go to the impact of climate change on water resources and water infrastructure. Then we talk about water and energy and access in urban environments. And then finally, we talked about resilient water management strategies. which is decentralized green water infrastructure systems and alternative water sources. And so that's kind of the content of today's talk. So yeah, please, next, please. So I wanted to start here, emerging 21st century problems. The first decade, cybersecurity in the aftermath of 9/11. And the second decade, recognition of threats caused by changing climate. In the third decade, implications of COVID-19. So this looks like different topics, but actually when we are trying to do a resilient water management strategy, so these are all connected sort of. So I'm not going to talk about the other topics, but we'll have to just keep in mind that everything is connected. And one of the problem is we always focus on one thing and we miss other things. So next slide, please. So briefly, climate change science encompasses climate change causes and effects, future projections of climate change and climate change consequences over long periods of time, years, decades, or even centuries. Climate change science is very complex. It's a cross-disciplinary science using the tools of atmospheric science, biology, geology, chemistry, oceanography, physics, and ecology. So it's a very cross-disciplinary area. But we don't go over a lot of things, but I just want to say a few things. So yeah, please, yeah, go to the next, yeah. So scientists have linked increase in Earth's surface temperature to atmospheric increase in greenhouse gases, carbon dioxide, methane, nitrous oxide, aerosols, water vapor. And if you hear the news or media and everything, total focus is on carbon dioxide, but there are other elements which are impacting the climate change. And so basically the impact is called warming the temperature of the Earth, and we call it the greenhouse effect. Next slide, please. Yeah, one before that, please. Go back to the before. Yeah. No, the next one. Okay. So this is the average surface temperature, which shows the increasing trend over time from 1850, which is about the time of Industrial Revolution. So it means things got started about the Industrial Revolution time when we started using fossil fuels. Next slide, please. So the Earth's global average surface temperature has increased about 1.4 degrees over the past 100 years. But the observation shows that the last 35 years has increased. Kind of the trend is increased. And climate change, what we think about it in terms of water, global precipitation pattern, ice melt, sea level rise, ocean warming, and ocean acidification. So these are the things we'll talk about a little bit. Next slide, please. So possible causes of climate change, solar radiation, and also it's not here, but volcanoes. Recent science shows volcanoes also had an impact on CO2 emissions in the atmosphere. Man-made or anthropogenic causes, human activities, fossil fuel energy, coal, petroleum, and natural consumption, animal waste, landfills, etc. So it seems like the total focus is right now on fossil fuel energy, but we have to be aware there are other issues. Here I have deforestation, which also kind of relates to land development, urbanization. And deforestation could be a major component on the impact of climate change, but basically nobody is talking about it, so we have to keep that in mind. Next slide, please. So forests store carbon, sequester, and CO2 from the atmosphere. So when we have a lot of deforestation, so what happens? The forests do not absorb the carbon dioxide anymore. So it goes to the atmosphere. So it could be a major cause of climate change. Recently in the news, there was a summit in Brazil in Amazon forest, a climate summit, which was on the top of the mountain. Basically, they removed 130 or 40,000 trees to pave the road to get to the summit. And so it's kind of something which is really totally ignored in terms of climate change, what is causing it, So we have to be aware of these things when we go to mitigation and adaptation strategies. Next, please. Next slide, please. So climate change evidence and observed evidences: ice melt, sea level rise, warming of the oceans, and ocean acidification. These are observed. And we totally trust the data which is observed, which I show you in some slides. Okay, next slide, please. So Arctic ice melt. So the National Research Council report notes that the average annual extent of Arctic ice has dropped by roughly 10% per decade since satellite monitoring began in 1978. I'll show you a satellite monitoring later, but satellite monitoring has really improved the monitoring of the water in different ways: sea level rise and water quality and everything else. Next slide, please. So this slide is also a little bit old, but you can see the boundary of ice in Arctic Ocean, and it's a little bit like less than year 2000 right now. So next slide, please. So global sea level rise, it's from 1955 to recent years to 2015. And at the end of the slide here, so you can see satellite imagery, so which is more precise. Next slide, please. And then here is the red part is the satellite imagery which is shown, but this whole thing is from 1880s to present time. So we can see that the sea level rise has happened. It's happened by about 8 inches, 20 centimeters, since the late 19th century. Next slide, please. So one of the impacts is ocean acidification. The direct observation of ocean chemistry have shown that the chemical balance of seawater has shifted to a more acidic state, lower pH, and that will impact, of course, the ecosystem in the coastal areas in the ocean. Next slide, please. So just briefly about climate change models are very complex. They are based on mathematical equations that represent the best understanding of basic laws of physics, chemistry, and biology that govern the behavior of atmosphere, ocean, and land surface, ice, and other parts of the chemical system, as well as the interactions among them. So climate models are like it's a science which is evaluating based on the supercomputers and availability and everything else. So next slide, please. So here we show like a slide, a typical example of different climate change models. You can see different type of trends with different climate change models, which some of these models like show the impact like 50 years or 100 years from now or something like that. So, and that's kind of a, next slide, please. A little bit questionable, although the results do not predict abrupt changes in climate, often referred as tipping points in the near future. However, warming process increases the possibilities of major abrupt change cannot be ruled out. Although the studies shows that if we zero the CO2 emission in the atmosphere today, which is a global thing from many countries, if it turns to zero today, nothing changes in temperature of the Earth 75 years from now. So that's something really keep in mind in terms of mitigation and adaptation strategies. Next slide, please. So just carbon footprint, the total greenhouse gas emissions attributed to fossil fuels produced by an individual, an event, a product, or an organization. So everything has got a carbon footprint. So the computer is sitting by the laptop, whatever it is, so it's got a carbon footprint. What you are wearing has got a carbon footprint. What we eat has got carbon footprint. Everything has got a carbon footprint, which we show it in tons or pounds of carbon dioxide. Next slide, please. So climate change resilience. So this is international. So there are two approaches: mitigation, actions taken to limit the degree of future climate change, such as practices that directly or indirectly reduce the carbon dioxide emissions to the atmosphere. So basically, globally, there is a lot of focus on that we want to totally eliminate or zero the greenhouse gases. And we kind of do not think of natural causes or anything else. So the focus is right now their international global focus. Adaptation and adjustment in natural or human systems in response to actual or expected climate variability, extremes, and changes. So my focus is more on adaptation. I think we are in a stage that, because of the resources and knowledge and everything else in the water environments, we should have a total focus on adaptation to climate change. So next slide, please. So the impact of climate change on water resources, I showed you the trends. Next slide, please, but I show you some slides. So water resources, well, we always work on a watershed basis and everything. So basically, this slide shows the precipitation pattern is changing or has changed. The sea level has risen, so we showed that. There may changes in evapotranspiration and that sort of thing. And there are changes in runoff that we'll show slides. And so rainfall changes or changed. Runoff is changing. The sea level rise is changing. So these are ice melt is changing. So these are the impacts on water resources we have to take into consideration. Next slide, please. So there's global effects on water resources, decline in long-term average winter snowfall and snowpack, and that's very important. We see it in, for example, the Himalayan region. We see it in Sierra Nevada mountain range in Western United States. So what happens when the snow melt pattern is changing? The seasonal amount of water in the river is changing because the snow melt is not happening as what's happening in the past. It happens throughout the year. So the river flow is changing or is changed. Some places are getting drier and some places are getting wetter. So when we are planning water management, so we cannot rely on a constant water level in the rivers. Next slide, please. So impact of climate change on water resource summary: erratic weather patterns, severity and length of droughts. In some places we get droughts, in some places we get too much water. Less total annual rainfall, less snowpack in mountains and earlier snowmelt. Increase in heavy precipitation events in some places. Sea level rise. And in my opinion, sea level rise is very important. I'll show the slides later. Encroachment of salt water into freshwater aquifers because of sea level rise and other impacts. And changes in ocean acidity and impacts on aquatic life. I showed you a slide on that already. Okay, next slide, please. So I wanted to show this slide in the B. So this is satellites are really advanced now. And the GPS system is very advanced. And so the sea level rises measured very precisely now. And also the satellites measure some water quality impacts on the coastal areas and other lakes and other places. So comparing to 15 years ago, so we have more uh, trustable databases based on new technologies that will inform us a lot more. Thank you. Next slide, please. So sea level rise in coastal areas, reasons. So thermal expansion of ocean water. Oceans are getting warmer. The water is expanding, so you get a sea level rise. Melting of large glaciers and ice sheets. We saw some slides on that one already. Moon's gravitational pull on Earth. And coastal urban stormwater runoff. Urban environments are kind of neglected. As I'll show you, we are kind of discharging a lot of stormwater runoff in the coastal areas. Could be a cause of sea level rise in the coastal areas. So we cannot separate urban development or urbanization from other factors, which I'll show you, which got a lot of impact on what we are doing right now. Next slide, please. So about 40% of the world's population live in coastal areas. And a coastal area is defined 100 kilometers from the ocean as coastal area. Next slide, please. About 50% of US population live in coastal areas. So our major cities are in the coastal areas. Our population centers are in coastal areas. So when we are dealing with water management issues, so when we are talking about water scarcity or drought or floods, everything. So I think a lot of focus will be on the coastal areas. Next slide, please. Typical coastal population. In Virginia, about 60% of population live in coastal areas. In Puerto Rico, 90% of population live in coastal areas. So based on that, island countries have major problems. Not only the people live on the coastal areas, but also because of sea level rise. Next slide, please. So in Virginia, we are in Virginia, so Hampton Roads area is a major coastal area, Chesapeake Bay area, so we are kind of focusing on that area a little bit. Next slide, please. So here is Fox Island and Chesapeake Bay. In 1776, the area was 426 acres. In 2019, the area of the Fox Island is reduced to 34 acres. So this has happened over time. As I said, if we blame the Industrial Revolution, it started about that time, so the sea level rising. Well, maybe other factors too. Next slide, please. So this is New Point Comfort Lighthouse, Matthew, Chesapeake Bay. And you see in 1885, the year is not sure, but about that time is a USGS photo, where the lighthouse was inland. In 2016, the lighthouse is totally surrounded by water. So this is a total of very good evidence of sea level rise in the coastal areas. Next slide, please. So sea level rise impacts salt flooding, saltwater intrusion, high salinity in tidal waters, high salinity in coastal aquifers, degrading vegetation and ecosystems. So these are like the sea level rise impacts. Next slide, please. So this is Norfolk, Virginia, and also in Virginia Beach. So we are observing these very often right now. So these things are happening as a fact. So our focus should be how we are going to adapt to these situations in the coastal areas, but also there are other areas in the country, like we had Ellen storm in last year in North Carolina. These things are happening also. So, but coastal areas, since majority of the population live in coastal areas, so it could be a major issue. It is a major issue Next slide, please. So I said a little bit about land and about aquifers here. Like you see on the left slide, you see how the water is moving back and forth in the coastal areas. But I want to pay attention to the right slides here, which there's ocean water, which is salt water. And on the left on this picture, you can see freshwater aquifer. So in the middle is saltwater aquifer. And two things are happening. When the sea level rises, the pressure is changing. So more salt water comes to the part which is half salt or something, and then it gradually intrudes into the freshwater aquifers, especially when we try to withdraw water. The balance is changing. The coastal aquifers are getting more salted. Next slide, please. Yeah, so again, yeah, I want to see that slide one more time. Yeah, the previous slide. Yeah, so water withdrawal. So what happens, like in the coastal environments, we have a high population, and we use a lot of groundwater. And also, as I'll show you later, we also cannot supplement the fresh groundwater, so salt water is gradually coming to the aquifers, and then these fresh aquifers getting more salty, and they will need more treatment. Next slide, please. So, impact of climate change on water infrastructure, drought, storms, and flooding. We saw some flooding and pictures in Norfolk and Virginia Beach area. So in some places, like the cities are above the sea level, so the flooding is more serious. Source water quality, eutrophication, and excess algae growth because of warmer temperature. Increased sediment or nutrient inputs due to extreme storm events. We talked about sea level rise. And general utility preparedness. So this is also very important, especially in coastal areas. We see the impact in places like Louisiana, which was a major storm, and the areas are flooded, and a lot of wastewater facilities and drinking water systems are impacted because of the flooding. Next slide, please. So about 1/3 of 505,000 wastewater treatment facilities in the US, and many drinking water sites are at risk of flooding in the event of a mega storm. Well, the first street, well, that's the source of this information. So aging infrastructure and lead pipes are also problematic, will be partially addressed. Well, these are addressed in the new infrastructure bill. But basically, when we are talking about infrastructure, we are not talking only about sea level rise or flooding or drought, but we are also talking about the existing condition of the system that I'll show you some slides now. Next slide, please. So I call it this inherited 20th century water management problems. Land development, which was basically done according to the science at that time, increased population density, problems associated with modern water infrastructure. So we have to take all these into consideration when we talk about resilience. Next slide, please. So this is one of my favorite slides, which shows, it goes only to 1992, around the East Coast, DC area, in these places, how the land was developed. In this 1992 slide, you still see some dark spots, but all those dark spots are filled now. So basically everything is like developed in the area. Next slide, please. So basically land development and population growth are like chicken and egg. When we develop the land, we proceed with urbanization because of job opportunities and other opportunities, other life standards. So a lot of people come to the city. And then when the people come to the city, the population increases. When the population increases, we build more apartments and more roads and more land development. So here is an example of Washington, D.C. The population in 1800 and now we see. So as long as land development is, I observe this in my local area in Blacksburg, Virginia, like every day a new apartment building is coming up. Actually, not with much consideration with green infrastructure or water management. So it's happening across the country. Next slide, please. So I said this already, 80% of US population live in urban areas. Next slide, please. So, and there's increasing trends. So there's also, when we talk about water demand, so we have a lot of competition. We have drinking water systems, we have food production, industries, commercial systems, ecosystem and recreation. We want to preserve ecosystem. And right now, ecosystem is impacted a lot because we withdraw a lot of water from rivers and lakes and groundwater. So water scarcity, we defined as a gap between available water supply and water demand in urban areas, which is a very emerging problem. Next slide, please. So urban characteristics, we have to be aware of these things. Urban, let's have less vegetation cover, increased paved and impervious areas, rooftops, parking lots, and roads. Because of that, increased runoff volume and associated contaminant loss to surface waters, increased flooding potential, decreased infiltration to groundwater aquifer, which are described in the next slide. Next slide, please. So this is one of my favorite slides. On the left top, you see about natural condition. We have only about 10% runoff, 40% evapotranspiration. We have shallow infiltration, and then basically we have like groundwater water supplied from rainwater. And as the urban development increases, the trees are gone, deforestation is gone. And this is a typical urban center, which we get about 55% runoff from urban areas comparing to 10% runoff, which is natural condition. And so it means that we decrease or have decreased quite a lot the natural infiltration, which supplies the groundwater system. So, and I always say groundwater is water in the bank, and we have to protect groundwater systems if we are serious about water management. Next slide, please. So impact of land development, floodplain. So floodplain is defined as we have here a stream or a river, and we have precipitation or rainfall, the water levels naturally rises, and it spreads around. So we call that a floodplain. And actually the floodplain is changed because of urbanization. And when there's a precipitation level, when the river flow increases, so actually the floodplain is expanded to urban areas because the water doesn't have any place to go. It does not infiltrate anymore. So the urban areas gets more flooded. So our definition of floodplain is kind of outdated because of urbanization. Next slide, please. So I showed you the slide how the groundwater flow is decreased because of urbanization. So these are some areas in Virginia, in Norfolk and Louisiana County, Chesapeake City, that the groundwater is decreased, mostly because of urbanization, lack of infiltration. And so saltwater intrusion, because of that, I showed the example why saltwater intrusion happens in coastal aquifers. And this is like coastal areas in Chesapeake area, but also Northern Virginia areas that aquifers almost empty right now, and it's not typical to Virginia. Across the country, aquifers are totally empty, especially in urban areas. And so we don't have a backup water system when a drought comes or something happens. We don't have a backup water system in urban areas to supplement the water supplies. So this is a very dangerous situation. So we have to always keep in mind the groundwater level and what to do about it. So in groundwater, like what we do or we did when groundwater declines, as I showed in the slide after the production, we dig deeper wells. Deeper wells, what they do, they extract water, but they use more energy. As deep as we go, we need more energy to extract groundwater. So and water and energy are very related. So I'll show it later. Next slide, please. So I want to complement the 20th century accomplishments, water management infrastructure, building dams and reservoirs, developing groundwater resources, constructing centralized water treatment plants in water delivery infrastructure, installing sewer and stormwater pipes to move away wastewater and stormwater from population centers, and eventual discharge to surface water where it goes, using significant amounts of fossil fuels-based energy to meet the critical need for water source development, water treatment, and long-distance delivery. So when we develop water sources, we use energy for water source development, I'll show you later, for water treatment and water delivery. So these are the accomplishments of 20th century, but it's got like some drawbacks. Next slide, please. Oh, no, next slide. This is this brief. Okay, yeah. So modern water if I summarize it, because we have three infrastructure systems: potable water systems, which includes water sources, water treatment and distribution via pipelines. We have wastewater network, which is wastewater drainage, treatment plants, wastewater discharge, and we have a stormwater runoff drainage network. So, which takes the stormwater runoff to surface water systems. So, if you are in an engineering program, so usually we have thought of these as separate systems. Like we have had courses on drinking water supplies, we have courses on sewage treatment and distribution, when we have courses in stormwater discharge. So they've been treated totally separately in the 20th century. But actually this now under the concept of one water, these are all connected. Our potable water system, when we use it, it supplies the wastewater network because all the used water goes to wastewater systems. And all the paved areas and everything else goes to the stormwater runoff. So these are really interconnected. We use more drinking water, so more population, so that impacts the stormwater runoff too. Next slide, please. So pipeline construction. So I call the backbone of water infrastructure pipeline. Basically transports potable water to population center, transports wastewater away from population centers. It transports the stormwater runoff away from population centers. The pipelines are very critical in water management. Next slide, please. So now I call this the dilemma of pipelines. There are an estimated 240,000 potable water main breaks per year in the US, 240,000 potable water main breaks, which is wasting over 2 trillion gallons of treated drinking water. And it's according to American Society of Civil Engineers. And then pipelines, although even if they are new pipelines, are not one piece of a pipe, but they have joints. Within the joints, there are leakage from pipelines, and there's a lot of water is leaked from the pipelines, even under good conditions. So pipelines are a major source of water loss. Let's think about it that way. Next slide, please. So I'm describing to you the problems because if we don't understand the problems, we cannot come up with solutions. So, and basically here, urban stormwater management, drainage network, rainfall, rooftop runoff, and it goes to a drainage system. If you look outside by your roadside, you can see the drainage system, which collects the runoff from parking lots and roads and also from rooftops. So, and rooftops constitute 30 to 40% of impervious areas in urban environments. So, next slide, please. So, stormwater runoff. I call it America's wasted waters. Well, probably it's globally wasted waters, but I'm thinking of Virginia and America's. They are America's wasted waters. That's something we have to remember. So, approximately 10 trillion gallons of year of untreated stormwater enters U.S. rivers and waterways. So all these from rooftops and drainage areas, it goes to urban drainage. And in the meantime, it collects a lot of contaminants from parking areas and roads and that sort of thing. So it's got a major impacts in ecosystems. Next slide, please. So we have, in US, we have two types of urban stormwater drainage network. Combined sewer systems, which basically sewage pipelines and stormwater runoff pipelines are combined. There are about at least 770 cities in the US. So we have a storm drainage. Well, actually, the sewer pipeline is there originally. We have a storm drainage, which connects to that. And it's got two drawbacks right now. And when there's a storm event, the system is overflowed, and when it's overflowed, it kind of it flows within the city. You know, the overflow goes to the city. We get a lot of contaminated water, like we got in New Orleans, for example, in the cities. And also, it exceeds when the pipeline flows. It exceeds the capacity of wastewater treatment plant to treat the water properly. So, but still, there are many cities in the US which have combined system. Next slide, please. So an example, San Francisco combined sewer and stormwater system faces challenges during heavy rains, discharging nearly 2 billion gallons of wastewater annually into the ocean and San Francisco Bay. So this is this year's data. Next slide, please. In Philadelphia, aging combined sewer system released nearly 14 billion gallons of polluted stormwater and untreated wastewater into local rivers and creeks in 1 year, according to data analyzed by the CBS News. So, and there's a need for investment, but on these systems, but we have to do the investment in the right way, as I'll be talking about it in a few minutes. Next slide, please. So the other than combined system, we have municipal separate stormwater sewer system, which we call it MS4. And basically, the sewer system sewer system operates separately. So the water is collected and is moved to a wet pond or river system or something like that through the pipelines. So this is separate system, which has become very common in America, in Virginia. So again, it goes mostly without treatment. It goes to river or lake. So it's a wasted water. So, and when we talk about alternative water sources, it becomes very critical. Next slide, please. So MS4 is not a combined sewer system designed to collect and transport the stormwater runoff using storm drains, pipes, ditches. Temporary water storage facilities do not sufficiently address water quality impacts of urban stormwater runoff, which has got a lot of contaminant. Not a part of publicly owned treatment works. And actually, this is a little bit changed now because in some parts in Virginia, right now we pay for stormwater drainage. So it was not a part of stormwater drainage until recently. Owned by a state, city, town, or village. So, but now We didn't pay before for stormwater management, but now in our bill, we pay some money for it. Next slide, please. So I give you as an example Hampton Roads, Virginia stormwater runoff. Hampton Roads is a major next to Northern Virginia, DC area, major area in terms of water use and in water, stormwater drainage. Next slide, please. So Norfolk, you see, well, this data is from Hampton Roads Regional Planning Commission. So you see 1 million gallons of water, stormwater runoff, which is generated in the area in Hampton Road within the Chesapeake Bay watershed. And here I'm showing only 3 big cities, but Hampton Roads has got like several other cities within the Hampton Roads, but the total here like includes other cities like stormwater runoff, that many million gallons of water in Hampton Roads area. Next slide, please. Yeah, so in Hampton Roads, stormwater runoff is about these many million gallons per year. And rooftop rainwater, which is about 30% of that, is this much. So these are wasted waters in Hampton Roads, which mostly goes to rivers or the Chesapeake Bay, right now. And this could also be a cause of sea level rise in the Chesapeake Bay area cities. Next slide, please. So let me talk a little bit about water energy nexus. So all water sources, developed water sources, use energy. As I said, in water development, source development, you lift up water from the river or lake, you treat it, you distribute it. So we know about that, but also energy is using a lot of water. Fossil fuels uses a lot of energy. And also I should bring to your attention that large solar farms also use a lot of water because of cleaning the panels and everything takes a lot of energy. And about 2 days ago, I saw an article from Virginia Tech researchers that the stormwater runoff from solar farms has become a major problem right now because it uses a lot of water and contributes. It's a research in progress, but let's keep that in mind. The big solar farms may also produce a lot of stormwater runoff. Next slide, please. So just to show you from 76 industrial revolutions, steam powered pumps, which came into, so this shows the trend of energy development in the United States. And there are, other than what we call renewable energy like solar and wind, hydroelectric is a major renewable or clean energy. And unfortunately, in recent years, for some valid and invalid reasons, the hydroelectric capacity is not increasing. But there's research now how to improve the efficiency of these systems, but that's something to keep in mind. I worked on a project which is called like small hydroelectric plants, not big rivers. Like you can produce, whenever there's pressure, you can produce electricity. In urban areas, it's got a lot of potential to produce electricity from hydropower. So more focuses on these right now. And nuclear energy has also got a lot of potential, but I think this will be developed. And other than these things we don't know about, other energy sources are renewable energy sources under development, which will probably change the picture in about 10 years. Next slide, please. So significant energy use moves water faster and farther from source to consumers. It's a major reason or a major for emergence of population centers because we can bring the water very fast to the population centers. Next slide, please. So fossil fuel-based energy consumption. So thermoelectricity generation is one, of course. Agriculture is a major source of energy use. Urban infrastructure and transportation, including air transport and water infrastructure. So our focus is basically on water infrastructure right now, but all these areas need energy use efficiency and other methods to reduce the carbon dioxide emission. Some real measures, to do that. So next slide, please. So energy flow and water infrastructure. You see, I said water resource development. From the river, we lift up the water. We use energy, and we bring it to treatment water systems. We use energy here, and we distribute the water. We have seen water tanks all over the place, pressure water tanks. We use energy to keep the water like pressurized and distribute it to residential areas, cities, all over the place. And then we have collection systems for wastewater from all our buildings and houses. The wastewater goes to wastewater treatment systems. And mostly we use a lot of those are gravitational systems. So we use gravity to transport the wastewater from the city center to like a treatment system. But then when a water treatment system, we use a lot of energy to treat the wastewater and discharge it back to the rivers. So this water is not like treated to the drinking water level, but treated quite a bit according to the established standards. But we still introduce a lot of pollutants through this as well, sometimes unknown pollutants, like use pharmaceuticals, for example. You lift up the water from here, it comes here, we use the water, and when we use the water, some pharmaceuticals find their way into wastewater, and they're not treated here. We discharge it to the river, and when you go back to the river, we pick up the water, so we got pharmaceutical, which is a big problem. But anyway, I just wanted to show you, but it came to my mind. I had to talk about it. So, okay, next slide, please. Water infrastructure energy consumption. So 70% use of energy goes to distribution and pipelines and storage tanks, and about 30% goes to water treatment. And this is the study we did in Blacksburg. And basically, this is very close to an average in terms of energy use for water distribution, and it depends on topography and geography. And some places, like I always think about New York and California, the water from California water supply source from for New York City is supplied from northern New York by gravity flow, doesn't use any energy. So, but in California, like they use Colorado River, the water moves through the mountains, everything. So the energy used in California is more energy intensive in terms of water supplies than New York City. So it depends on topography. But on average, like about a lot of water is used for water distribution. Next slide, please. So, and how we use the water. In general, about 2/3 of the high quality and energy intensive potable water that the utilities produce is consumed for non-potable uses, such as flushing toilets, washing cars, and landscape irrigation. Next slide, please. So in the US, about 4% of total energy use goes to water and wastewater, and 4% doesn't look like a lot, but US is a major user of energy. So we use a lot of energy in water supplies and wastewater treatment that we have to find ways to conserve energy and reduce the carbon emission if we think it's a major problem. Next slide, please. So we did, yeah, so this is for coal, petroleum, and natural gas. Obviously, natural gas is a less producer of CO2. In a lot of places are switching or have switched to natural gas. Although in some places there is some resistance to that, which is not good. So anyway, so natural gas is a cleaner gas comparing to carbon dioxide in terms of water consumption. Next slide, please. So we did some work on like in Blacksburg area, carbon footprint of water, like carbon emission in pounds per day, and so we can do it. It depends on where you are, but in average, 0.25 to 0.35 kilowatt hour per 1,000 gallons of water. The carbon emission, it depends on the locality, but that's an average, and Blacksburg, Virginia falls in about an average level. Next slide, please. So carbon footprint of water consumption building. So Y Center in Blacksburg is a very small building. We calculated the carbon footprint for that. And also we did for one building, and a campus building at Virginia Tech. And this is only for one building, and Virginia Tech has got hundreds of buildings. And a university campus is more like a city center because of high population density, dormitories, and everything else. So they could be a major source of carbon footprint. And unfortunately, even we build new buildings on campus, we do not think of this at this time, you know. So next slide, please. So, okay, so I want to go faster because the time is not. Okay, so I just show a table that's published 20th century goals in 21st century. I showed you the examples of waterworks in 20th century, and we are moving a sustainable system. Here on the wastewater, we want to have zero pollutant discharge. The stormwater runoff, we are moving from wasted water to land, low impact development. And water source development, we are moving or trying to move to alternative water sources, stormwater, wastewater, stormwater, wastewater reuse, and salt water. And energy we are moving to renewable energy. I showed you the emerging problems in my first slide. So next slide, please. So basically the technologies, the technologies which we used in the previous century is not adaptable to this century. And here I show you transition 21st century ingredients for holistic approach. Science and technology is evolving. Practice is evolving, like in some places more than other. Policy and regulation is moving ahead, but is not keeping up with science and technology. Education, kind of evolving, but really not keep up with science and technology. And public perception is not keeping up with technology. And I gave you one public perception. A lot of people think that river water is very, very clean, comparing to an advanced wastewater treatment system which produces drinking water, which is not true. Our rivers are highly polluted. As I showed you the slide, it gets a lot of wastewater. It gets a lot of stormwater. So river water is not basically clean. Let's put the recycled water, you know, nowadays. Next slide, please. So the technology strategy developed is not adaptable anymore. So next slide, please. The paradigm shift, the philosophy. Water problems are local problems. Solutions to problems can be sought at the local level using holistic approach. Minimizing using water using pipe network. for transportation of water and also energy into and out of urban environments. Using locally available water, alternative water sources, which is rainwater, saltwater runoff, gray water, salt water. Plan and design and implement integrated natural and engineered systems. Implement energy use efficiency and renewable energy. Energy use efficiency is really, really important. So at this time, next slide, please. So elements of climate resilient water management strategy, water conservation. As I showed you in the water energy nexus, all the water we use uses energy. Every drop of water we drink is used energy. Every drop of water we waste, we waste energy. So water conservation is really critical. Water quality management, energy conservation is really important. Flood control, drought management, food security, food water energy nexus, disaster preparedness, and this is really important, sustainable water systems. And sustainable water, we think of economical and technological feasibility. With resilient, we also include like disaster and food security and all other issues comes under resilient, more than sustainability, which is a trend for 21st century. Next slide, please. So climate change mitigation strategies, energy conservation in utilities and industry and infrastructure, housing and transportation, policy options and incentives to encourage energy conservation and reduce gas emissions, green technologies, and education. So we have to focus on all these things, and conservation should be our major issue, rather than like forcing any utility to totally move to renewable energy within 2 years or something like that. It's not possible. That will cause drought and other problems. But conservation is really critical. Next slide, please. Adopt agricultural production methods to changing climate conditions. Adopt cities to changing climate conditions. That's what we are talking. Prepare to cope with droughts and floods, water energy use efficiency, transfer it to renewable energy resources. Next slide, please. So climate change mitigation, water sector, water and wastewater utility energy efficiency, curtailment of or environmental behavior. So we did, this is very, environmental behavior is very important. We did a study in dormitories, for example, at Virginia Tech, a controlled dormitory and others. So we found that there's a lot of water could be wasted in dormitories, which, as I said, a dormitory at university campuses like city center. So even in homes in every place, environmental behavior is important, not only in water conservation, but also energy conservation. When we don't turn off the lights, we use energy, so always we should turn off the light. So adopting water saving fixtures, this is also important. If you buy a washing machine now, comparing to 10 years ago, so it saves more water and energy. So and all these things reduce the carbon footprint of water consumption. Next slide, please. So how to reduce carbon footprint of water consumption? I say already, potable water saving is equal energy saving, water conservation behaviors, fixtures. We'll talk about rainwater capture use later. So utilities, utility energy use and efficiency. We have to, utilities should move toward that direction. Some utilities use, New England, there are few utilities use renewable energy for water treatment now, but it's not a nationwide thing. In the Middle East, a lot of renewable solar energy used for water treatment of salt water. But in America, still we are far behind. Next slide, please. So the need for developing novel holistic approaches that integrates natural and indigenous systems, solutions that recognize nexus between water, energy, and food production and environment in urban environments. Next slide, please. Holistic and water energy management can be attained by implementing small-scale decentralized energy infrastructures. This is what I'm promoting, and decentralized water energy infrastructure. This is what I'm promoting like these past 10, 15 years. Next slide, please. Functions and advantages of decentralized water infrastructure enhance the potential of using locally available alternative water sources. I showed you how rainwater and stormwater is wasted, how gray water is wasted. We can use that. Salt water, our major population centers are in coastal areas. Salt water has got a major use. So although it's like a piece of a puzzle, like we are not trying to totally like move on rainwater, stormwater. It should be a combination of all these three in urban areas. Whatever is most feasible, that should be studied. Energy conservation for decentralized systems, like I showed you the pipelines. If we use decentralized systems, like using locally available water, there'll be a short distance for water transport. We use this energy. Enhances the potential for locally available renewable energy use for water treatment and delivery. As I said, there's a major problems with the large solar farms, but if you're using locally available renewable energy as a decentralized system, that's very valuable. It could be used for water treatment. It could be used for desalination of water, for example. We could use also for gray water treatment. So it's got a lot of potential if it's a small scale and locally based. Enhances cybersecurity. I mentioned cybersecurity in my first slide. Our major big treatment systems, water treatment systems could be hacked or threatened a lot. So decentralized system reduces that threat quite a bit. Next slide, please. So integrated decentralized water systems. So basically, we collect the rainwater from the rooftops, from the surface areas. We use it indoor. We produce wastewater. We produce the stormwater, and we have a storage facility. So basically, it goes to a treatment facility. It uses, for example, solar PV. And then we treat it, and we bring back the treated water, use it. So this is an ideal vision for a treatment system. One thing that I've not talked about is like groundwater recharge. A lot of stormwater runoff could be recharged to groundwater because we have empty aquifers. Right now, maybe it's happening in one or two places, but it's not happening much. So this is the vision. Next slide, please. So this is a small water treatment system. Advanced small water treatment systems uses reverse osmosis carbon filters and UV light. Allows treatment of rainwater, stormwater, wastewater, saltwater, anything at the local level. So we should see in the future a lot more of these systems, which we see a little bit right now. Next slide, please. So locally available alternative water sources, rainwater and stormwater runoff, saline water, which is disinfection in use, desalination in use, and gray water. So because of time, I'm focusing only on rainwater and stormwater, and but this is a major area. I've worked on this also about 15, 20 years or something like that. And green water is happening across the country, but yeah. So next slide, please. So green water infrastructure systems, also bioretention system like rain gardens, porous pavements, green roofs. Use of rain gardens are very good, but they are very limited. Porous pavements are also got limitations. We don't say that they should not be used, but they should be used where feasible. And green roofs too. They should be used where feasible, but they are limited. The rainwater harvesting, stormwater capture and uses has got a lot of potential. So I want to go over a few examples of that. in community gardens and urban agriculture is very useful, is a futuristic approach. Next slide, please. So green water infrastructure systems. So as I said, the conceal uses stormwater runoff, and I talked about locally available water, and also I said something about micro hydro, and geothermal is also a big renewable energy source locally available. And the future should be focused on these things too. Next slide, please. So just a few slides about capture and use of rainwater and stormwater runoff. Next slide, please. So rainwater harvesting played an important role in water supply in early civilizations. Since 2500 BC, quota pipes or clay pipes were used to collect the water and use it. And so there are other cases. And in this slide, on the right side, this is historic in a sense that it started me on rainwater harvesting. This was 1998. We published a report on rainwater harvesting. You cannot see it here, but this is a mountaintop in Southwest Virginia in Dickinson County, which is also a coalfield county, and water availability is very limited in mountaintops because it's very expensive to lift up the water. There could be a public water line like about 1,500 below this mountaintop, which is very expensive to lift up. And also groundwater is impacted a lot by mining activities. Actually, mountaintop communities, they are using a lot, we call system, collect water, and they are disinfecting the water and using it. So it is a popular method there. So this got me started, and then we looked at other issues. Next slide, please. So as I said earlier, rooftop areas constitute 30 to 40% of impervious areas in urban settings. And so this shows a typical rainwater harvesting tank. And this is important to know. 1,000 square feet of rooftop area can collect 620 gallons of water per 1 inch of rainwater. So 1,000 square feet can collect 620 gallons per 1 inch in an area. For example, maybe Chesapeake Bay is 43 inches, so you multiply that for 43 inches. So that's why the amount of potential rainwater in Hampton Roads area is so high. Next slide, please. Yeah, so I showed this one already. So rooftop area in Hampton Road area can collect this much water, which is right now is almost ignored probably. Next slide, please. So potential uses of captured rainwater, outdoor uses, potable water saving, lawn irrigation fountain, indoor non-potable uses, mostly toilet flushing, laundry, cooling. Cooling is very important. Indoor potable water use, potable water saving. We can use rainwater for potable use other than the system which I showed you. We can use other small advanced technologies to use it for indoor uses. Community gardens and groundwater recharge. Next slide, please. So there are some examples. I show only a few example rainwater harvesting case studies. Like this is a school which is using it for flushing toilets and that sort of thing. It shows the amount of water which will be collected there. Next slide, please. This is rainwater harvesting for laundromat, which is in a jail in Roanoke County, Virginia, which is collecting a lot of rainwater for laundry. And actually, its rainwater property is much better than natural rainwater for laundromat. So this is another example. Next slide, please. So this is like it's a small house, residential rainwater treatment system for potable use in Key Largo, Florida, which we studied a few years ago. So these type of treatment systems are available to use the rainwater indoors for drinking water purposes. And this is a house, but of course it could be used for that school or for a larger building as well. Next slide, please. So rainwater treatment depends on the purpose of water use. For potable indoor uses, as I showed you, carbon filtration, we have pre-filtration, carbon filtration, activated carbon and UV and other for disinfection and that sort of thing. For non-potable uses, so you don't have to do advanced treatment, but if you have to treat it, you have other methods to use, which are now getting popular for outdoor uses, pre-filtration only. So, but the guidelines are available. Next slide, please. So, potable water energy savings is an example. The middle school which was the water used for landscape irrigation. So we calculated harvested rainwater, estimated energy saving, and estimated carbon reduction. For the regional jail, which I showed you, this is estimated energy using, and this is the estimated carbon reduction. So this is only for one facility. If we install rainwater harvesting facilities in a lot of places, buildings, so you could see that will be quite increased. The carbon reduction will be enhanced. Next slide, please. So overall benefits, I talked about it already. Reduces stormwater runoff, flood control, reduces potable water use, reduce energy consumption, fossil fuel-based energy use, supports local food production, enhances urban aesthetics, groundwater preservation and drought management. Okay, next slide, please. So I've got a few minutes to talk about food, water, energy, and access. So food production totally depends on water and energy. As I said, water and energy depends on each other, but food, you cannot produce any food if you don't have energy, if you don't have water. So nowadays they call it FEW, food, energy, water, FEW. Next slide, please. So rainwater harvesting case studies. So this is in urban agriculture. I want to show you a few slides. Next slide, please. So it could be a community garden, it could be a home garden. This is in our publications. Next slide, please. So the thing is, like urban agriculture is getting popular, roof garden is getting popular, but we are still using potable water, So in terms of water consumption, that defeats the purpose. So we have to come up with integrated systems which uses rainwater for urban agriculture. Next slide, please. Yeah, so in this case, integrating rainwater harvesting urban agriculture, so which is the study in Roanoke, that we have examples that could be copied elsewhere. Next slide, please. So also the advanced technologies are getting applied to rainwater harvesting system. You can use GPS system, geospatial analysis, to identify or find the areas which has got potential for rainwater harvesting, for example. Next slide, please. So this in Roanoke area, so geospatial technologies were used to look at all the buildings in the area and the areas which we could install rainwater harvest system, where we could do rainwater, where we could do urban farming. So we can use advanced technologies for urban development, for new methods in urban development. So this is in case in Roanoke, Virginia. Next slide, please. So urban scale stormwater management. So we had a lot of focus in the latest slides on rooftop rainwater, but urban scale stormwater management is really important. It's a part of wasted water in Hampton areas and other areas that we should collect and use. So this is the groundwater capture, stormwater for turf irrigation in Washington, D.C. Next slide, please. Okay, this is ornamental water feature at the Cincinnati Zoo, which is replenished by captured rainwater. So these are some good examples. Next slide, please. So I just saw this one last week, which when I was preparing the slide, which is November 21st, 25. The plan for converting the golf course for a stormwater park in Virginia Beach. This is like really, really good. I got excited. Things are coming to Virginia and Virginia Beach, to Eastern Shore, and I think it'll take a couple of years to complete I think it's 2027 or to complete this project. So this is really, really exciting. Next slide, please. So this is something which I want to promote, groundwater recharge in coastal aquifers. And it should not be limited to coastal aquifers. As I said earlier, like our aquifers in Northern Virginia and all across the country are empty because overdraft of the groundwater because of urbanization. So groundwater aquifers are empty, and I said groundwater is water in the bank. So we are instead of discharging all that produced stormwater runoff to the rivers, which impacts river ecosystem because of contamination, we should do like minimal treatment and find treatment ways to recharge the groundwater, to the stormwater to groundwater. So here we have recharge wells, which salt water comes here. So if we have recharged water here, it creates a boundary between fresh water and groundwater. So interestingly, I'm coming back to these things. I started my PhD studying groundwater recharge, and at that time I found out that in Long Island, New York, there are a lot of groundwater recharge to prevent the saltwater intrusion in the coastal aquifers in Long Island, and it's a very popular method in Israel too. So it's got a lot of applications, and after many years, I'm coming back to this. So it's kind of strange. Next slide, please. So imperatives. These are the renewable energy, geospatial technology, information technology. Our curricula should become a cross-disciplinary water management in the coming years. Maybe it's happening somewhere, but it's not happening that much. There should be courses which covers all these areas. Next slide, please. So challenges and impediments, traditionally conservative attitudes within water resource and engineering planning community. I notice resistance by utilities for using rainwater, rooftop rainwater, or promoting rainwater harvesting, because it reduces the dependability on utility water. So we should find ways in terms of community planning to bring the utilities together with decentralized system, or make the decentralized systems a part of utility system to make it more efficient, the system more efficient. Silo mode college curricula and water management. As I said, we need to upgrade the college curricula. We need to work on policy gaps and hurdles. There are a lot of policy gaps and hurdles. There's a lot of our policies are influenced by certain interest groups in one way or other. So we have to find ways to come with objective ways to develop policies. Public perception, we need education in both graduate level, undergraduate level, K-12, and citizen education. Next slide, please. So this came to my attention a couple of days ago. Successful climate resilience strategies must include robust planning, leadership, and the collaboration of public and private sectors to create long-term, adaptable solutions for growing environmental risks, which includes changing climate and urbanization and everything else. So from my interaction with my colleagues, I work a lot in Southwest Virginia, coalfield counties. I had a colleague who had a lot of leadership, a lot of wonderful things were happening there, and want to see that type of leadership. Probably the leadership is not in Virginia Beach, that stormwater pond is maybe a result of a vision by a leader there. We need those things. Next slide, please. So I like this quote: the future is already here, it's unevenly distributed. The example of case study I showed you, it is happening, but we want to see it happen everywhere, not only in a few places. Next slide, please. So we did, during the last few years, we did a few books. And this book is, I think, 2 or 3 years ago, probably 2, 3 years ago, Resilient Water Management Strategy in Urban Settings, Innovations in Decentralized Water Infrastructure Systems, which includes like systems from examples from other countries and also systems in the US. So we compiled as a book to promote decentralized water infrastructure. And this is alternative water sources for producing potable water, focuses on potable water, which includes chapters on using gray water, seawater, stormwater runoff, rainwater. So all case studies, innovative approaches are kind of outlined, which shows like a road to the future of water management in urban areas. So, and the next slide, please. So this book was just produced this summer, Smart Technology Applications in Water Management. I showed you one example in terms of geospatial technologies application for urban planning. Also, we have like machine learning or data science applications in stormwater management. We have robot use in urban use. We have there are other methods. I mean, with satellites and all sorts of technologies, which we have examples in this book, how it could be applied to urban water management. So hopefully this show a trend toward people or instructor professors looking up these books and integrating it all there as a reference book or a teaching material in their classes. And also planners should pay attention to these new technologies in new literature, which is available right now. Next slide, please. So the time we planned for 10:30 12, the time is 12:01, and I think I can, yeah, if the time allows, I can take a couple of questions. If not, it's all up to Trish in the Resistance Virginia, but this is my email and also the website. Please feel free to contact me if you need more information of something which I said was not obvious. When we rush your speaking, it kind of skips stuff, but hopefully I didn't skip stuff, and I raised my objections to some certain things, and I supported some things and showed a roadmap to future water planning management, especially in water areas, water management, urban water management. So, okay, Trish, I think that's my conclusion.
Right. Yeah, that was great. And I'm okay staying on a couple minutes if anybody wants to stay on and ask a couple of questions. I know we're after 12, so you're welcome to hop off. We can send out slides after this too. But if anybody has a question, feel free to raise your hand or unmute. So, uh, Dana, or Dana, I'm not sure how, I'm sorry, I said your name wrong.
Hey, thank you for the presentation. Really appreciate all of this. Some of us who are trying to help Goochland County put in some protections for their data center development. Some of us have been against the data center development, but it looks like it's gone through. And so we would like to help the Board of Supervisors set up regulations to prevent discharge of things like biocides and heavy metals, and then also ensure that they use municipal water instead of well water, because 85% of the residents in that county rely on well water. So do you have any recommendations um, on proactive measures that the Board of Supervisors might take in regulating data center development?
Well, I think in Virginia, the wet states, I think rainwater is a major source of water. It should be think of a source of water, a water source. So I think they're probably collecting the rainwater from the area, from rooftops, everything will help the data center in terms of to not rely totally on groundwater or import the water from other places. The rainwater harvesting should be included as a part of planning the water management in the area. So yeah.
Thank you.
That interact with
Somebody wants to talk?
in our very urban area where there are can yeah there's a resource protection area protect streams, but instead there's some big substation. I'm curious about overall downstream that much impervious surface. So close to, in this case, it's going to be basically supplanting the resource protection area because utilities are a permitted use in stream valleys. So I'm just curious about where I can find resources or how I can look at this from the downstream and water-related impacts. That will help me with my advocacy.
I couldn't. I don't know if everybody did. I couldn't catch the first part of your talk.
Oh, sorry.
Yeah.
So the fact is that in Fairfax County, in a particular
Which county is
watershed
it?
that is very urban,
Yeah.
Fairfax, can you hear me now? Fairfax.
Yeah.
One of the, I mean, there's the data centers that are impacting directly upon the streams that they are, in terms of impervious surfaces and deforestation and all of that. How I can kind of come up with something relevant that local lawmakers can understand about. I mean, they know their business better than I do, and the county staff, but not the elected leaders. I'm just trying to find resources for understanding how that much impervious surface and deforestation in an urbanized watershed can be measured, that kind of impact.
Yeah, I think there is probably in terms of policymakers, maybe it's too much. I think we should have workshops which focus on legislatures because
Yep.
yeah, and also it's really good. You talked about downstream. It's really good to get the schools involved in terms of water monitoring and that sort of thing. Get schools involved to monitor the water downstream. How is this impact or something? Definitely, we need to get more like solid programs for K-12 to be involved when they reach to college level. So they know a lot about the water and the importance of water. Everybody just thinks water comes from the faucet, let's drink it and that's it, and you just do a survey of school or anybody where your water is coming from, probably 80-90% of people wouldn't know where their water is coming from, so there should be more educational citizen level education programs at the school levels and legislature levels and all sorts of things, so yeah. yeah, above ground natural. Of course, deforestation is a major source of carbon dioxide increase and urban heating and everything else. So I think there should be a lot more focus on on forestation of urban areas. I think, yeah. So and still, I mean, we are planting trees here and there, but still, it's not a national movement. It's not even a regional movement, you know. So
I think the question I liked in the chat, which I you partially answered, but it sounds like the guy was asking, is there a one-to-one substitution of, say, storage tanks versus, in a particular site, storage tanks versus forest in terms of their efficiency of dealing with the runoff?
forest and what? What's the other one?
Let me just go back to the question. You can see the question. Actually, I can't find the chat anymore.
Okay, trees are very important because they also could be used as a buffer to the streams. So if trees are planted by the streams, they have the functions to pick up the pollutants which are coming from roadways and going to the stream. So that's one function of the trees. And of course, a lot around here, I also see students are planting a lot of trees. That's for stream protection is very important. But a lot of people don't realize it's also good for CO2 emission, you know. So trees could have a lot of functions, and it's not only making the place green and livable, but also it picks up the contaminants from water, tree roots, and also picks up CO2 from the air. So trees are very, very, I think, very critical for urban development.
Luke, if you want to unmute, if you can unmute, if you have other questions on your comments and question in the chat, you're welcome to. Okay, he said that's a valid answer. Okay, thank you. I just wanted to make sure.
Yeah, sometimes it's hard to understand, like the noise, sometimes hard to understand the questions, yeah.
Mhm.
So
Does
very
anybody
good.
else have any questions? If not, I did drop his email in the chat also, and I'll send out the slides.
Well, if necessary, we can share the PDF copy of the slides.
Yes,
If
yeah,
somebody's interested, I can share the PDF copy of the slides. Not the
that would
whole
be
thing.
great.
The
No,
PDF copy can be posted on the website. So yeah.
yeah, I'll definitely share a PDF copy of the slides. A lot of people were asking for them. And if nobody else has questions, I think we can let you all hop off.
Yeah, everybody's mostly gone now. Okay.
All
Thank you
right.
very much all.
Thank
Thank you
you,
for your attention.
everybody.
Thank you.